Hello, and welcome to this presentation, Understanding VNAs Cable Impedance Measurements. In this presentation, we'll explain how to measure the characteristic impedance of a coaxial cable using a vector network analyzer and the Smith chart. This presentation assumes a basic understanding of the Smith chart. If you're not familiar with the Smith chart, or if you'd like a brief review, you might want to watch the presentation Understanding the Smith chart before beginning this presentation. Let's start by reviewing coaxial cables, or coax. A coaxial cable consists of three parts: an inner conductor, a conducting outer shield, and an insulator or dielectric material between them. The entire cable is also usually covered by plastic insulation. The characteristic impedance of a coaxial cable is a function of the diameters of the inner and outer conductors, as well as the dielectric constant of the insulator between them. There are many different types of coaxial cable, but most are designed and manufactured to have a characteristic impedance of either 50 ohms or, less often, 75 ohms. In many cases, the labeling on the outside of a coax cable can be used to determine the type of coax and its characteristic impedance, but a vector network analyzer can also be used to measure the characteristic impedance of an unknown or unlabeled cable. The characteristic impedance of a coaxial cable can be measured using the quarter-wave impedance transformer principle. A quarter-wave impedance transformer is a transmission line which is a quarter of a wavelength long, and which is terminated in a known impedance Z sub L. In this case, the line's characteristic impedance, Z sub 0, can be calculated from the known value of Z sub L and from the value of Z sub in measured using a vector network analyzer. Using the quarter-wave impedance transformer equation and solving for Z sub 0 produces a simple equation for calculating the characteristic impedance of a quarter wavelength line using known Z sub L and measured Z sub in. Our measurement methodology has 4 steps. The first is performing an open short match calibration on the VNA. Given that we're often only trying to determine if a cable is 50 ohms or 75 ohms, high accuracy is not usually required, and this step can often be safely omitted. The next step is attaching the cable and terminating it with a 50 ohm load. We then configure and run a reflection or S11 measurement on the port connected to the cable. As we'll see, the start and stop frequencies of our sweep must be properly set. And finally, the results of the measurement are plotted and interpreted using the Smith chart. Let's look more closely at this last step. If the cable and the load impedances are both 50 ohms, a dot, or a very small circle, will appear in the center of the Smith chart. This behavior generally occurs over a wide frequency range, although the dot may get slightly larger as the maximum sweep frequency increases. What happens if the cable and the load are not both 50 ohms? In this case, the trace on the Smith chart will create either a partial circle or multiple circles as shown here. This kind of trace would be seen if a 50 ohm termination were connected to a 75 ohm cable. Note that the length of the trace is a function of the sweep range, that is, the user-configured start and stop frequencies used when making the measurement. In order to determine the impedance of our cable, we want to configure these start and stop frequencies such that the trace crosses the resistive or prime axis one time. The start frequency for the trace is not critical in measuring cable impedance and can usually be set to 100 kHz or even lower. But the stop frequency must be set high enough that the trace crosses the resistive axis one time. For example, this trace has too low of a stop frequency and does not reach the resistive axis. This trace has too high of a stop frequency, leading to multiple crossings. But this trace has an ideal stop frequency where the trace crosses the resistive axis one time. The ideal stop frequency in megahertz can be estimated by dividing 75 by the approximate cable length in meters. The 75 in this equation is 1/4 of the speed of light in millions of meters per second. Note that since signals propagate more slowly in cables than in a vacuum, this mathematically estimated upper or stop frequency will result in a small amount of overshoot past the resistive axis, as shown in the Smith chart on the right. Once we have an ideal trace on the Smith chart, the next step is to use a marker to determine where the resistive axis was crossed. This purely resistive value will be used for Z sub in, and is 120 ohms in this example. Note that in many cases there may not be a trace point that falls precisely on the resistive axis, but using the next closest point will still yield acceptable results. The final step is then calculating the characteristic impedance of the cable using this measured value of Z sub in and the known value of Z sub L, which in this example produces a measured cable impedance of 77 ohms. Let's end with a brief summary. Most commercial coaxial cable has a nominal characteristic impedance of either 50 ohms or, less commonly, 75 ohms. This can often be determined from markings on the cable itself, but it can also be measured using a vector network analyzer and the Smith chart. The steps in measuring cable impedance with a VNA are as follows. First, perform a standard one-port open-short match calibration, and then terminate the cable with a 50 ohm impedance. Then run a standard S11 or reflection measurement with suitable start and stop frequencies, and plot the results on a Smith chart. If the result is a point or small circle near the center of the Smith chart, the cable's characteristic impedance is 50 ohms. Otherwise, use a marker to determine the point at which this trace crosses the resistive axis. And finally, use this equation to calculate the characteristic impedance Z sub 0 using the measured value of Z sub in and the known load impedance value Z sub L. Although we've used coaxial cable in this presentation, a similar methodology can be used for some other types of cables as well. This concludes our presentation, Understanding VNAs, Cable Impedance Measurements. If you'd like to learn more about VNAs, other VNA measurements, or Rohde and Schwarz network analyzers, please see the links in the video description. Thanks for watching.